So there we go. Cool. All right. So we want to do that. We want to just jump into assembly. Can you guys handle that? Is everybody ready for some assembly? It's been a couple of weeks. Are we ready to learn more?
Yeah, we got a little bit of bit manipulation and shifting here to do.
All right. Actually, I got to pull it up now. I've got to get the document open. So give me just a second here. I had it downloaded. Now I got to get it opened. Very good. Yeah, I'm looking forward to getting back on target here and learning more stuff. Yeah.
Is this the most people you've had on video-wise?
Since we've been on Zoom, possibly. So what do we have? 4 by 3, 12 people on right now. Myself means 13. This might be one of the bigger Zoom turnouts since we've switched over. Definitely. It is definitely a possibility. All right, so we are going to go ahead and we're going to switch over to the full screen view here. And right now we've got Ron Delvaux on camera, but I think as Steve starts talking, we'll get Steve's camera on here. But we are now here on part 6 of our assembly language series. Part 6 comes right after part 5 for those of you who are not up on your numbers yet. And here we go. Take it away, Mr. Bjork.
Oh boy, oh boy, oh boy. Anyways, one thing that when you do graphics, you do sound, you check I/O, you're looking at things on a computer, is a lot of times the stuff isn't a full byte, it's a bit. It's just one unit of information, whether it's on or off. And this part of the lesson has to do with manipulating information, not in bytes, but all the way down to the bit level. A byte contains 8 bits, and you got to deal with it. And not only is this important for, putting graphics up on the screen and playing with the 6-bit audio and stuff like that, it's, it's really part of also helping the computer making decisions. In other words, testing information and responding to it. So we'll be talking about decision making in the next session, but this section allows us to set up and figure out what information we want to look at so we can figure out what we want to do. So let's go ahead and dive into bit manipulation and shifting commands, and let's go with the next slide.
There we go.
All right. Sometimes you're going to get information in the byte that you don't want to deal with. And one of the easiest ways to remove that information is using the AND command. We've all heard people say the phrase this and that. It basically means that you want to say that your answer is if both of them are together. In other words, if you compare a 1 to a 1, you get a 1 out of it. If you've got a 0 to a 0, you get a 0 out of it. If you compare a 1 to a 0, guess what? You get a 0 out of it. In other words, both bits must be 1 to get a 1 answer, get the 1 out of it. Now, in the case of the AND command, that can work on the A and B registers, which are your 8-bit registers, or it can work on the condition code registers. Now, that's something we're going to save for a later time, because condition code registers are things like the flags, like whether or not the answer was 0, if you had a carry, and a few other things like that. So we're just going to concentrate mostly right now on using the AND instruction with the A and B registers. And of course, when you use this operation, all the flags, or I should say the flags of negative and 0 will be set or reset depending on whether bit 7 is set. Well, that's the negative. That's what the negative flag bit works with. And if all the bits are 0, then the 0 flag will get set. And for some reason, the overflow flag will get to 0 automatically for some reason. But anyways, really basically what it's doing is it allows you to strip off information. And like, for example, if you are looking, oh, that was lovely, that burp.
It must have been David at his.
Yep. Couldn't get to that mute button, could you? Anyways, for example, one of the ports on the Coco is the status of whether or not, of the RS-232 bit on the bitbanger port, for the input. And sometimes you'd like to be able to just see if that particular bit is high or low for the status of what it is. Well, what you would do is use this AND command to strip away the other bits by having them 0 and leave that one bit that represents the serial port 1. And what that does is when you do the command, the answer is you either get a 0 or 1 only on that one bit. So this is very, very handy for doing input information and also, and also clearing bits and stuff like that. So it'll be something that as we get into the practical use of assembly section of the course, we'll be using quite a bit when we go to the next one. As I said earlier, the AND condition code is used to clear bits in the condition code register. We'll go into there's some very special function commands that we'll go into later. Now, one thing I will mention about this is a lot of other processors, they'll have a command such as clear carry flag and set carry flag and all these other type of bit manipulation flags where they're a direct command to either set or clear it. Well, the 6809 with all of its addressing modes and instructions like that, it was starting to get ridiculous on the number of individual commands. So they decided to use AND condition code for all the different clearing of carry flag, overflow flag, and all the other flags in the register. It was a way to save on the number of commands that were in the system. So
it also has the advantage that you can set or clear more than one flag at a time, which on other CPUs you have to issue multiple instructions to do that.
Exactly. Very handy when you're doing high-speed interrupt instructions and like that too. So it was a way to get rid of a lot of these commands that aren't used too much, that are just single function commands, and make it where in one command you do a lot. And the only downside to it was the fact that we had basically, an extra byte, because you have the command that says we're going to do this, and there's a byte embedded in the command that says which flags are you going to clear. So anyways, we're going to get into more details about the condition code register when we go into the special function commands in a later episode. So let's go to the next slide. This here command OR is the exact opposite. It's used to set a bit. It's used to make a bit become 1 in a lot of cases like that. It's, like AND was this and that. Well, this is OR this and that. If either bit that matches is a 1, you're going to get a 1. You only get a 0 when both bits are 0. So bit 0 in one location is a 0, and bit locations 1 is 1 in another, you're going to get a 1. If they're both 0, you're going to get a 1. Pretty simple and straightforward. And a good example of it is down at the bottom of my slide here, where we've got a number, this is in binary, of 0, 0, 0, 0, and 1, 1, 1, 1. In other words, 4 zeros, 4 ones. You AND it with 1, 0, 1, 0, 1, 0, 1, 0, and you're going to get 1, 0, 1, 0, 1, 1, 1, 1, 1. In other words, everywhere that you have a 1 in the bit, you're going to get a 1 out. And there are times that you want to do this too. Like, for example, if you put information out on the 6-bit DAC, well, that's only 6 bits. Well, Tandy used the other 2 bits for stuff on that I/O port. And one of those bits is the serial output bit. So if you were, and you have to set that bit to 1. If you don't, what will happen is that as you change the audio, you're going to be sending data out your serial port, and it's going to be a bunch of garbage. And if you have a printer connected to it, it's going to print to your printer. So what we would do when we'd create the audio that we wanted to go out, that 6-bit audio, before we put it out to the port, we would do an OR %10, or in other words, the number 2. And that would make sure that bit stayed high and wouldn't mess up the printer. And yes, some of the early games did screw up your printers because some people didn't realize to do that. So,
learning has a curve.
Yep.
Yeah.
So, well, you start learning how all this stuff gets done. Anyways, let's go to the next slide.
Steve, I just want to go back to that slide. Did you have the results of the OR and the ante samples at the bottom? Aren't those backwards?
For an OR, you're right. No, I have it right.
Because your AND example there should be 000011111, shouldn't it?
Okay, let me go to my AND. I may have made a typo. No, the AND is correct.
For your result?
Yeah, for the result. The AND is correct for the result, and so is the OR.
The AND will only turn on a 1 if both bits are 1. So in this case here, the only times
there's the problem. In the slide, I have the word AND when I should have put the word OR.
Okay, yeah, that's what I was wondering.
Yeah, that's exactly
okay. So OR favors the 1 either way, but AND only favors the 1 if both bits are 1.
Yeah. Exactly. And I apologize for the mistake there. I think I was doing this slide a couple weeks ago at 2:00 in the morning.
That's why I was kind of hesitant on questioning it here, because I haven't had much sleep the last couple of weeks due to work either. So I wasn't sure. I was thinking
that's exactly what it is. So anyways, well, let's pass on to the next slide after the OR.
Roger that.
And of course, we have the OR condition code, which is used to set the flags. As Chris pointed out earlier, you can set a bunch of flags all at the same time and like that. But we'll talk more about that in a later session. Let's go on to the next slide.
We'll save that for an after dark.
Trust me, I have one lesson already planned where I'm going to try and get you to at least DEFCON 2.
But I wanted it DEFCON 5.
DEFCON 5 is the coolest one. DEFCON 1 is the hottest, so
yeah,
it counts down.
Yeah, they had that argument on Big Bang Theory. Anyways, now this command, EOR.
Oh, that's a Winnie the Pooh character.
Yeah, this is not Winnie the Pooh character, but it is. Think of it as either or, because what happens here is if the bits don't match, you get a 1.
Is that the exclusive OR?
Yep, exactly. Basically what we're doing here is it's very much like the previous ones. It operates on the A and B registers only. No, they did not put this in as a condition code setting or resetting instruction. That would have been ridiculous. But anyways, basically the idea here is if you want to flip a bit. This is real handy for in the case of, let's say you got something on the graphics screen and you want to change it, and you can use this flipping of specific bits and like that. So only one dot changes, even though there's 4 other dots in that particular byte and other things like that. But also there are times in working with the IO ports when you're reading them like that, you want to flip the information. Also, if you're using the single bit sound port, you use the EOR to flip it, to change it from high to low, low to high. Okay. And basically, any bit that's set, by the way, this slide has the same problem too. The word "and" appears in the example. It's supposed to be EOR. But,
okay.
Yeah, but the results are what they're supposed to be.
So we've just recently been joined by Simon Jonason. I believe he knows a thing or two about 1-bit audio. So Simon's probably familiar with this.
Yeah. Anyways, but once again, it's only on the A and B register.
Okay.
And it's very handy to change things and like that. And that's one thing you do in the processor a lot is you do go through and have to change the status of bit quite a bit for things. And the reason why we do a lot of bits is bits, there's 8 bits in a byte. That saves a lot of information. When you only had 64K of address space, you really had to go down to the bit of information. A lot of programs I use, not only was there compression, there was ways where, okay, I only needed 8 states for something. So that's 3 bits. Well, within a byte, I would use 2 different things that had 3 different states. That way I got closer, I could put in half the space and I still had 2 bits on top.
Right,
and there's also other techniques with that we call data streams. And we use that quite a bit in audio and like that, where it's, the bits don't line up with bytes. So you have to go down to bit manipulation. So we do an awful lot of that. See, nowadays with our computers, we got so much damn memory. We don't care about getting down to the bit. So let's go to the next slide.
Let me just ask you a quick question on this one here. So if I was to visualize this, because we're talking about literally inverting bits,
right?
This could be used to create like a inverse flashing effect. Like if you had white text on a black background and you were just to EOR all of these, you could simulate the inverse blinking, right? So black on white and white on black?
Right. And you could even go farther. If you had 4-bit color, you could switch between 2 particular colors and other issues and like that. It's a very handy command, but you got to remember it's going to read the information and flip it, and it's going to only do this in the A and B register. So the A register would have to read the memory location, flip it, flip those particular bits, and then store them back out. So you have to do this, move the information from the screen, put in the CPU, flip the bit, and then move it back again. And the next instruction will show you how we can do it faster.
Okay. Next slide.
Can I chime in there? If I know this is not, we've not done this yet, but a lot of vector graphics, if you want like filled vector graphics, you make a wireframe, and people actually use EOR to fill the vectors, because the wireframe is your bit that's set, and the bits that are not set get EOR'd, so you fill the vectors. I don't know if that makes any sense.
I think so. So you're saying if you have like a white outline for a cube, the black center, because the center is all black, if you ER that, what was black becomes white.
Yeah, so you get a face.
Yeah,
Gotcha.
we already talked about that earlier. Yeah.
Gotcha.
Let's move on.
That's cool.
Let's move on.
Okay.
All right, because I wanted to stay on the point. You're interrupting in the middle of a point. See, there's a command called comm. Complement basically means flip the bits. It's kind of like automatically EOR all the bits. It's taking the bits and flipping them all. Now, unlike the previous ones we talked about, where they really only work on registers inside the CPU, the A and B register, this will work with a memory location. So if you are pointing to a location on the screen and you do complement that location, it flips all the bits. So it quickly grabs the information for the screen, flips it inside the CPU, and sends it back in one instruction. You don't have to do an instruction to load it, an instruction to flip it, and then an instruction to save it back. So this works very quickly to do this inverting on the screen that you're talking about, Steve.
Yeah. The one caveat of this one, though, is that it does the whole byte only. Like you can flip the whole byte at once. You can't specify,
Exactly.
I only want the right half of the byte or the left half or whatever. That's the one restriction.
Okay, help me understand the definition of flip here. Is that the same thing as inverting, or is this like turning it up, making it?
This is flipping. Anything that was a 0 becomes a 1. Anything a 1 becomes a 0.
Okay.
And
Gotcha.
so it will flip or change the color on the screen extremely fast. So
Okay, so
Once again,
this is an EOR at a byte level that can go anywhere besides a register.
this is a full EOR where it's going to flip everything.
It's the equivalent of doing an EOR string FF, which means every single bit is set. So it's exclusive ORing the entire byte, all 8 bits only. You can't tell comm to only do certain bits in a byte. It always does the whole byte. But it's the same equivalent as an EOR FF, except it's faster and smaller.
Okay.
Yeah, and the thing is, when they were designing the 1609, the engineers really did talk to programmers about the type of thing they do and they want to do. Now, there's two philosophies in instruction sets. You want to sometimes bring information to the CPU, play around with it, send it back out. Other times, you want the CPU to be directed to do something to memory. And they knew that this flipping, this inverting of all the bits was going to be something very handy. So they made sure that it wasn't just a comp or complement A, complement B. They allowed you to complement to a memory location. And that would speed up the operation. In other words, I would say that using the complement instruction to flip the entire screen opposed to using the EOR would run at least not just twice as fast, maybe 3 times as fast to do it, because you don't have to bring the information in, flip it, and then send it back out again. In 3 instructions.
Right.
Instead, you're doing it in 1 instruction, so it's much faster.
Cool.
Yep. So very, very, very handy. And my examples down here, at least I got this one right without a typo, is comp A, comp B, and comp $7. Now you could probably tell with those 3 slides, I kind of duplicated the slide and was changing things. So sorry about that, folks. I'll make sure that Steve gets the typo corrected version so that when we put together these lesson plans that you can download from the web, it'll be correct. Sorry about that.
And the reason we brought it up is if anybody watches the video and doesn't have the lesson plan, and this is the way they're consuming it, that at least the corrections in the stream and are aware of it.
Yeah.
There you go. All right, we're on the next slide. The bit.
Okay. All right. So the bit command is very similar to the AND command. It works only on the A and B registers, though. And the difference is it only sets the 0 flag. It does not change what's inside A. The bit, in other words, the way to look at it, it's like a test. It's testing those particular bits to see if they're a 0 or a 1. Once again, this would be very handy for that I/O port that's got all these different bits on there, besides looking at the status of the incoming RS-232 bit, if you want to see where you're at. So you would have the bit pattern set up so that the only bit that had a 1 was the RS-232 input. And you do this instruction, and lo and behold, the Z flag would be set if that bit was 0 and would not be set if it was 1. So you would be able to know whether or not the status of the RS-232 input port was high or low. Once again, I/O ports, very similar to the way they thought about memory. There's not many of them. It's very restrictive. And so we have to go down to bit level. That's why so many things are tagged in on the. Also, the other thing, too, is when we're building the color computer way back when, we used these PI, peripheral interface adapters. And they had 2 ports essentially on them and for I/O. And you had 8 bits per port. And you didn't want to add chips just to do one function. That would raise the cost of the machine. So you try to put as much as you could on there. And by the way, the Coco used 4 ports or 2 of these chips for all of its I/O function, which includes the keyboard. But anyways, I think that one's pretty straightforward. It is doing the AND command without actually changing the stuff that's in the A or B register.
Yeah,
it only
that's really useful when you're
flag.
when you're handling hardware, let's say like a PIA or something else where there's multiple bits that mean different things, and maybe depending of this bit set, you want to go to this subroutine. If this other bit set, you want to go to a different one. This allows you to load in the status register, for example, and then go through each of these checks saying, okay, this bit set, then I got to go here, this bit set. And it doesn't mean, or it means you don't have to reload the register to check the next one. Because if you did an and you masked off all the other bits, well, now you've destroyed the original content. So if that bit you were looking for the first subroutine was not set, now I got to reload it again to get it back. Well, in some hardware cases, as soon as you load it, it resets to whatever the next value is going to be. So you've lost that, permanently. You can't properly handle it. The bit command means you load it once and then you just keep checking the bits as you go through without having to reload it or resetting the hardware, etc. So it's very handy to have this command, especially dealing with I/O stuff.
Yeah, it can be sometimes a nightmare dealing with the peripheral interface adapters when you're dealing with interrupts and stuff like that. As what Curtis is pointing out here is that you read it, it clears the flag that told you what in the hell generated the interrupt, and it's just, you don't want to keep doing that. So it helps, so the engineers, that back in Motorola, they made the PIAs in addition to the microprocessor, so things generally work hand in hand pretty well, and they give you instruction. And plus the thing is, as a programmer, you don't want to have to keep reloading something over and over again. I go, didn't I just do this?
Yeah.
The bit command helps you from doing that quite a bit. Anyways, I think we've covered that. I mean, it does make sense, Steve, doesn't it?
Yeah, I think so. So you want to check. If bit 7 is on. The answer is going to be in the V.
You would have exactly. So what you would do in that particular case, you would say bit A, $%, 1 followed by another 8 zeros, 7 zeros. Excuse me,
7 zeros. Yeah.
And then it would the Z flag would be set or reset based on the status of that particular one bit. And of course, since you're looking at a bunch of bits there, you could check several bits to see if any of them got set. This is extremely handy for the keyboard, because before you do a keyboard read, you've got bits coming down from your keys, and if you could check all the bits at once. Another thing is, most people don't realize the same hardware that does the keyboard and the Coco does the buttons of the joysticks. And that can be an issue, because if you press a button on the joystick, it can screw up what you read on the keyboard. That's the reason why the keyboard stops working when you press a button. Now, there are techniques to kind of get around some of this and like that, and we do it in video games, but man, it can generally be tough dealing with keyboards and joysticks at the same time.
Yeah, I think that was one of the things in Color Basic 1.0. If you actually pressed a joystick button, you saw a string of characters show up on the screen.
Yeah,
exactly.
all seven bits coming back from the keyboard on that matrix row would come back and print on the screen, so you could add A, B, C, D, E, F.
Yeah. It's just being a cheap way to get the stuff in there. And now you see how hard it was to get joysticks working on the Coco? Now you see why they didn't put it on the MC10? Yes, I got to get my weekly dig into that MC10.
You got to get at least a couple, because you haven't been on in a few weeks. So.
Yeah. But, yeah.
All right, so with this same command here, if I wanted to check, let's say I wanted to check the top 4 bits, I would do a bit of an address, and I would do like 4 1s and 4 zeros, and then the Z flag would tell me which bits were on, or would give me 4 1s if all 4 bits were on.
Well, what it would do is if any one of those bits was a 1, then it would tell you that.
Oh, so I couldn't compare multiple bits within a byte. It's just one single answer. It's just a 0 1 is the output.
Yeah, you can check multiple bits, but your answer is based on that group of bits as a whole only.
Gotcha.
So as long as if any of one of those 4 bits in the example was a 1, then it would be a non-zero.
Yeah, basically in his example here, it's checking to see are any of the lowest 4 bits set. That's what it's returning your compare based on.
Yeah. It's just like the AND. If you AND it together, the answer would be all 0 unless any one of the bits in the A register in that lower 4 bits was a 1. If one of them was 1, then you would get a non-zero response. So you could look for a bunch of bits at once if they're all 0.
Yeah.
No, there is no command that does the same thing if you're looking for any of the bits were. They don't have a version of this that emulates the OR command.
Okay.
But most of the time, they felt this was very handy. As I said, again, this is a situation where the engineers knew that they had a limited number of instructions. Well, first of all, if you look at a single byte command, let's say that all the commands in the entire 6809 were just 1 byte starting, that was the command section. Well, you could only have 256 commands. Trust me, there's a lot more than 256 commands in the 6809 instruction set. So They have what they call alternate pages, and they kept, like 10 hex was what they consider an alternate page, and it shifted the instruction a little bit. Instead of using one register group, it'd use another register group, or it'd be doing something else. Probably Curtis knows it more in detail because he loves playing with that stuff.
Well, 609 extended it further past that. Yeah, I'm quite familiar with it.
Exactly. So, that's the thing is, commands that were going to be used more, they kept it so that it only needed the first byte to figure out what the command is. But in the case of commands that probably wouldn't be used as much, they went to a 2-byte system just to get that extra number of commands that they needed. And, of course, part of it was they had to leave a few things out that make sense if they had put it in. And we're going to have one of those a little bit later that I'm going to harp about when we get to bit shifting. Speaking of which, let's go to the next slide.
I'm trying to. Hold on. Boom. Here we go.
Well, no, that's good. We had backed up. So one more.
Yep.
Bit shifting. Basically, we have sometimes when we're working with things, we have to move bits around within a byte, up or down. In other words, we got to make them so that they go up 1 row of bits or down 1 row of bits. And we'll get into exactly what that means in a moment. But there's 3 different styles. There's logical, arithmetical, and rotate. And they're all different ways of how you kind of shift information around inside of a given byte. And that's the thing is, with the 6809, we look at shifting things around a byte. And Curtis, I forget, the 6309, did they add 16-bit shifting?
Yes.
Okay. So we'll even emulate that on 6809. Got to remember, this thing was designed, back before the 80s.
8 or 79, yeah, because it came out in 79, I think, if I remember.
And a lot of the stuff was kind of new. I mean, it's amazing what these people were producing back in the day without a lot of computer. I mean, yeah, computers did help them. They had big mainframes and stuff like that, and many mainframes and such. But still, considering how little computing power they had available to them compared to today, what they were able to generate is amazing.
Yeah.
So, any case, let's go to the next slide. And what we're going to do is we're going to start with the logical shift to the left. This basically means that we're going to take every bit that's inside of a given byte and we're going to move it to the left. What that means is we're going to move it to a larger place. Bit 0 goes to bit 1. Bit 1 goes to bit 2, and et cetera across. And this only works, well, this works on the A and B register, also works on memory location. This is similar to that complement command where they knew this would be important and you'd probably play around with it and have to shift memory locations too. So why bring it into the A register, shift and send it back? We're going to give you the ability to do it directly on the memory location. Now, as I said, every bit is moved to the left or greater. That's what we mean by left. It means that we're basically 0 becomes 1, 1 becomes 2, and 7 goes out of the byte. And what we send into it, because it's logical, is we send in a 0. So bit 0 will always get a 0 as we shift in when we use this instruction. All the flags are going to get set like before, and in my example, if I got this example right, we have a pattern that I show of 4 1s and 4 zeros as a binary number. And then when you get done, it's going to be 3 1s and 5 zeros.
Right, because the left bit got pushed off, and then the right bit gets replaced with the 0.
And this is where binary mathematics come in very handy. Understand why the computer uses them. Because if you want to multiply this number by 2, you simply do a logical shift to the left. Think about it.
Yep.
I just multiplied that number by 2 by shifting it. This is faster in general cases than trying to do an add. Add a number to a number. That's another way you do a multiply by 2. And if you want to multiply by 4, you shift it one more time.
That goes in powers of 2s.
Exactly.
Right. That's how binary works. Yeah.
Yep. So yeah, once you get used to binary and you see how it works, you understand why a computer uses it and why it's so handy. So how did I do explain this one?
No, that one was real easy.
No, the one thing I want to point out is, and you mentioned on the slide here, is that the high bit, the one that's getting shifted out, goes into the carry, and that becomes critical for checking things. You can use that to check to see if the high bit's set, for example, without doing an AND. But also if you're doing longer multiply by 2s, etc., then the carry, definitely you need to keep track of that.
Yeah, you can see that the carry is not only used for doing mathematical stuff, such as you add 2 numbers and you get a carry. We remember all doing math by hand in school and like that. Of course, now we all use calculators, so why we do math by hand anymore, I don't know. Anyways, the thing is that, the carry flag is used to hang on that bit of information that would have been lost normally. And
I'm sorry to interrupt, but if bit 7 gets moved to the carry flag, does it occupy bit 7 location in the carry register?
Oh no, the carry register is a single bit.
Oh, it's just 0 1.
Yeah.
So it becomes true or false.
The carry bit is just 1 bit out of the condition code register.
Oh, so it's not a register.
No.
Yeah.
Yeah. It gets thrown into the carry flag, and that way you have a status of what came out of it. And there are times that in bit manipulation and dealing with stuff, we actually will use this instruction just to get the status of that 7th most bit if we don't care what happens to the rest of the register, or if we're using something called data streams, we'll do this shift to get the information that we need out of the data stream. So like the stuff that's audio music, that's stored as a data stream, and we just shift the bits over, and it's this style of bit manipulation that's used to take something where in the bit stream might only be 5 bits, so we'll shift it over 5 times, and now we've got our 5 bits, but we still have the other bits in the data stream that we haven't wasted. So when we shift another 5 bits from the data stream, we'll get that. And this is part of the reason why bit manipulation is so important for microprocessors.
Okay.
All right.
Almost sounded like you said bit mutilation there for a second, but yeah.
Trust
if you
me,
do it wrong, that's probably...
Yeah, that's the thing is when the code's gone crazy, I've seen some weird stuff on the screen. And by the way, in Canyon Climber, you know how the screen shakes when you go up the canyon? That was due to an error in manipulation. Yeah.
Okay, mutilated.
I was manipulating the graphics mode, or I should say, you'd hit the graphics mode and manipulate and go, ooh, that'd be a cool effect. Yep. Any case, if I haven't got you off of DEFCON 5, let's go to the next slide.
We're ready. Now we're going the other way.
All right. Yep. Logical shift to the right. This does exactly the opposite. It's going to take all the bits and slide them from the high to the low. It's going to shift in to the 7th bit as 0. In other words, just like we had the lower bit come in on the other side, it was a 0. We're shifting in the higher bit to the 0. So bit 7 goes down to 6, et cetera, where bit 1 goes down to 0, and bit 0 goes into the, what is it, Steve?
That's the compare.
No, carry flag.
The carry flag, yeah, carry flag, right.
Goes in the carry flag. And so in my example that I have down at the bottom, we have 4 1s followed by 4 zeros. We do the shift and we get a 0 followed by 4 1s and 3 zeros. In other words,
yep. So this time what we're carrying is the low order bit instead of the high order bit.
Exactly.
Yeah. Okay, so the carry in this case would be false.
That would
we're
be
just
clear.
moving a 0 into it.
Yeah,
okay.
Yeah, it shifts a 0 out into the carry, so the carry bit is now a 0.
Okay.
So we haven't lost the carry. The least significant bit, the 0 bit, we haven't lost. It's holding the carry in case we need it. And this is also very handy to do a divide by 2. But I must clarify this. Before in one of our lessons, we talked about signed and unsigned numbers. This is very handy for an unsigned divide by 2. So, in other words, normal math. Anyway, but you can divide number by 2, and you could figure out what the remainder is in the carry flag.
Yeah.
Straightforward. Let's go ahead and go to the next slide so we can get to a different style. Arithmetic shift to the left. This is the one I want to complain about. It is identical to, it is literally, physically, the same command as logical shift to the left. They just named it differently, but it's the same number. So
same opcode?
Same opcode. It's physically the same command.
I think it's just to make it so that if you're thinking in terms of arithmetic shifts versus logical shifts, that you have the congruity of having both versions in your command set. But yeah, literally when you assemble it.
But this does not do a arithmetic shift to the left. It kind of does it, and when we get into the next slide, I'll explain why.
Okay.
Let's go to the next slide. All right, the arithmetic shift to the left. One of the things that it does, arithmetic shift to the right. Let me get that correct. I did a typo, just speaking. Anyways,
that's a Spico.
Yeah, it's a Spico. What it does is shifts all the bits to the right, similar to our logical shift right, except for one thing. Bit 7 does not move. It stays the same. While it may be copied from bit 7 to bit 6, bit 7 stays there. It does not change.
Okay.
The reason why you do that is bit 7 tells you whether or not the number is signed, if it's negative or positive. So you don't want to change or shift that bit. You want to hold on to the sign. So basically, bit 7 goes down to 6, 6 goes down to, etc., all the way down, where bit 1 goes to bit 0, and bit 0 goes in the carry. But the main thing is bit 7 doesn't change. It holds its position. And so in our example down at the bottom, we've got 4 1s followed by 4 zeros. When we do the shift, we actually get 5 1s
right,
and 3 zeros, and then the carry flag will get cleared because that was a 0 in the last bit. Now, this is very handy for doing a divide by 2 if it's signed.
Meaning you want to track if it's positive or negative?
Exactly, you want to hang to it.
And
now,
the high order bit 0 would be negative, positive, and 1 would be negative?
Yeah.
Yep,
and this way it always keeps that signed bit. So if you're dividing by 2 with ASL, then it's basically treating it as assigned. So that top bit that says whether the number you started with was a positive or negative number stays the same. So if you take -4 divided by 2, it's -2. It's still negative. Whereas if you did a logical shift, which would throw a 0 in there, all of a sudden that bit changes. So if you tried to use that to do a sign divide, it would suddenly end up being -4 divided by 2 is +2, which is wrong.
Right.
And this is where I had the problem. Go back to the previous slide.
Okay.
Remember I said this is the same thing as the logical? The logical always takes the lower bits and moves them up higher, period. Yeah. So what's in bit 6 goes into bit 7. If this was used for arithmetic shifting of a signed number, whatever was in bit 6 would be copied into bit 7 and destroys.
So you couldn't track the positive or negative.
So when I say that I'm kind of upset about this one, they didn't do it right. The engineers messed up here. And I'm sure their software programmers are a little pissed at them, as I am, that they did not truly put a real arithmetic shift to the left instruction in.
It sounds like we need to get Alan Huffman to record a jingle for Why Did Motorola Do That Now? So.
You got it. You got it. So this is one of the really important things to understand, is that while you can use this one to do signed information shifting down, that don't expect the arithmetically shift to the left to operate the way that the arithmetically shift to the right works.
Yeah, that makes no sense. You add the same commands, but one of them works properly, the other one doesn't.
Yeah, they should never put their put that in as a name for a command. It doesn't do what it's supposed to do. Right. So it's a beef I got with the processor, and it's the one that's kind of a gotcha for a lot of folks, because they'll sit there and they'll do this and you go, wait a second, what happened to my sign? Why did my number go from negative to positive all of a sudden? You know, it is something to be a watch for. So it's you got to be careful about that. In any case, we're getting close to being done here. Okay. We only have one last set of shifting instructions, and these are pretty handy too. These are rotate, and what's different about these is they're rotating through the carry flag. It is almost as if you're doing not an 8-bit rotate, but a 9-bit. They're considering the carry as part of the 9 bits of information in between the 0-bit and the 7-bit. Think about it like rotating in a circle, around the clock. So once again, these work on the A and B registers and a memory location. In this particular case, where we're moving to the left, every single bit moves to the left. The 0-bit, which is the rightmost bit, gets its information from the carry flag. And the 7th bit, when it gets moved out, goes into the carry flag. So no information's lost. See, like on the other one, you were always like shifting a 0 in. No, now you're shifting in the carry flag. So if we look at our example that I've got here, where you got 4 1s followed by 4 zeros, when you do the shift, you're going to get 3 1s followed by 4 zeros, and then whatever was in the carry flag will be moved into the bit 0. And this is really handy when you're dealing with numbers that are bigger than 8.
Okay.
If you have, let's go to the next slide because it really explains it well. Actually, one more. This is where I talk about this information where, you know how we've talked about before, the A and B register is really also the D register with them two combined together. It's a shorthand for the 16-bit of the two numbers. Right. Well, if you wanted to, say, shift both of them and carry that information, you would do a logical shift on the B register, logical shift to the left B register. That would move a 0 in, but it would move the 7th bit into the carry. Then you would do a rotate to the left B, and that would rotate the carry flag in to the lower bit of the B register and move everything up. So this way you can shift the entire 16 bits of information without losing any of the bits. So this is where the rotate comes in. It allows you to use the carry flag to move information that would otherwise been lost. And I'm sure Curtis has spent a little time using rotates inside OS 9.
The beauty of it is that because it lets you rotate through the carry, no matter which direction you're going, you can move bits between bytes basically as you're going across, shifting. As Steve mentioned, that's good for doing the D register because you can only do rotates and shifts on 8-bit registers on the 6809. But this also works if you're on memory locations, like if you're dealing with fixed point numbers or 32-bit integers or something like that, like a 4-byte number, you can keep going across. You can go from the least significant byte and rotate it into the second least significant, then rotate into third, rotate into fourth. And there's no limit. You could do a number that's literally 64K long and divide it by 2 by just rifling through and rotating all the way through. So you can do any kind of size of numbers this way. And this is used a lot in math routines. I can tell you, like Basic 9 uses it for integers. It does the 2-byte version. It uses it for the floating point, which is a 5-byte number. I think Basic, if James was here, somebody that's more familiar with Color Basic than I am, I'm pretty sure the floating point routines in Color Basic do this too, where it uses 5-byte rotates if you want to multiply a number by 2 or whatever.
Exactly. So, yeah, we're dealing with larger than 8 or 16-bit information, and it just allows us to shift it around. And there are times that I've used quite a bit in the video games where my position information is a 24-bit number. A good example of that was Axon. I'm flying around in space, and I have to figure out where I'm at. And trust me, 256 does not cut it. But the reason why I use 24 is I do fractions. The top 16 bits is the whole number. The bottom 8 bits of that 24-bit number is my fraction. And that allows me to have more smoothly moving things gracefully falling, stuff like that. But also in the case of Zaxxon, I was calculating a 3D environment, and then I converted it down to 2D for the graphic display. So the ship, when it was moving along that long fortress, it was moving thousands and thousands of dot coordinates as it moved along. It wasn't moving, something that could be held inside an 8-bit number. So yeah, it is. And sometimes there's these rotations you have to do in the calculation of the information, and the combination of logical and rotate allowed me to accurately do the calculations. By the way, for calculating the distance of a hypotenuse in things like Zaxxon and other games, there's no square root inside the 1609 processor. We're never going to cover that because it doesn't exist. And we all know that if you double A, double B, the square of one, square of the other, add together in square root, that gets you your hypotenuse. Well, there's another trick in math that you can do. If you take the longest distance of the side of the triangle, and you take the shorter side and divide that shorter side by 2, add them together, you are within 10% of the actual hypotenuse, which is good enough for pairs of collision. And
I actually made a spreadsheet recently just to check that out. Smaller values of the small value are a little bit over, but everything else falls right in place between them.
But it's within 10%, so it's good enough. It's good enough for video game work. Anyways, the thing is, how do I get half of a number? I do shifts. I do my shifts and rotates. Shift to the right, I get my half number so much faster than trying to calculate a square root.
Yeah. One other thing I want to point out too is this is really handy for doing things like screen scrolling. Because if you want to say take a P mode 4 screen, which is 1 bit per pixel, and you want to shift the whole screen to the right or a chunk of the screen to the right or the left, you do the logical shift and rotates to go through so it carries it through the bytes. And then you can actually shift portions of the screen left and right on a pixel level. So it's very handy for that kind of thing too.
And that's part of what I wanted to really say about this lesson is you can just see how much we bit manipulate a byte to get the stuff to do things on the Coco. It's everything from I/O to graphics on the screen. It's this is why they put this stuff inside the CPU, because they know that you're going to do a lot of bit twiddling.
Yeah. But graphics is one place where you really use this a lot, because, I mean, if you're drawing a font that doesn't fit on an even byte boundary, or you want to shift part of the screen left to right, or, it's just all kind of, or manipulating large numbers. I mean, all that stuff is done through bit shifting. So these are used actually quite a bit. You're drawing fonts on the screen on a high-res mode. That's exactly how it does it.
Yeah. So, we may start off this lesson where some people say, why would I want to learn about bit shifting or bit twiddling? Well, you're starting to learn just how much you're going to be doing that. You're going to be twiddling your bits.
Twiddling your bits.
Like you're twiddling your bits, like you're twiddling your thumbs. You're going to be twiddling bits. Let's go back one slide because I do want to cover the rotate right. It's almost identical, except for we're going the other direction of the previous one. Like before, you can do it on the A and B register, and you can do it on the memory location. As you can see, this designers of 1609 said this would be an important instruction where you would want to do it directly to the memory, not have to bring everything into the A and B register to manipulate it. Everything gets rotated to the right. The carry bit gets moved into the seventh bit all the way down. And then finally, when the 0 bit, that gets moved into the carry flag. So you're set there. And as our example before, we're looking at the 4 1s followed by 4 zeros. That would become the carry flag, whatever status was there, followed by 4 1s, followed by 3 zeros. And then the carry flag would have been cleared. So simple, straightforward. They just go in the different directions. If anything else in this lesson that I hopefully got through to you, arithmetically shift to the left does not work.
So just ignore it.
Yeah, just never use that mnemonic. Never use that command, and you'll be fine. I just had to talk about it because every single reference you're going to find on the 6809 talks about that instruction. It's not there. It doesn't exist.
Actually, Dave Phillipson just pointed another reason for bit shifting. We've covered that. It covers in graphics and doing streams of data. Compression, decompression uses it a lot. And he mentioned bit shifting is also used to reassemble the bits that come in from the bit banger port, like if you're doing a serial port, like with a modem or something.
Yep.
Because you only get one bit at a time. So how do you build your byte? Well, you load the bit in, you shift it in, and then you shift in the next bit. You keep building your bits up until you got a full byte. Then you can store the byte in memory. I've got my ASCII character that came from, Neil's BBS or something like that, and you just keep repeating that over and over.
Yeah, and the thing too is, even in modern computers, we found that it's actually faster to stream data. Your serial ATA drives are on your computer.
Mm-hmm.
They use serial. That's the whole thing. They use serial data, and because they're a simple serial line, they could actually transfer the data faster than the old style ATA drives, which were parallel.
Mm-hmm.
It's just that they could streamline how they could do the information, clock the data even faster, and boom. I mean, if you look at the difference between the size of the cable on a serial ATA and the old-fashioned ATA, one's a big, fat, thick ribbon cable that's got interference and capacitance issues, and I could go through I could go through all the engineering things that are just so screwy, trying to make it go faster and faster. And then they finally said, "Oh, God, this is not going to work." They came up with serial ATA because the old system was just pure trash, trying to go that fast. So. It always fascinated me because when I first started learning about this kind of stuff, I always thought parallel would be way better because, I mean, if I want to write a byte to a printer, why wouldn't I just write one byte rather than have to send out 8 individual bits? Because it makes sense. I mean, that instruction's faster. But you got to remember, at the hardware level, you've got to sync those bits. You can't have bit 7 showing up a couple microseconds too late because now it's on the next byte to the printer. You just scrambled all your data. Now you're trying to print a capital A and you've got a capital Z or something, or Z. Exactly.
I mean, physical limitations.
Yeah, with serial, you always know you only have one bit. So if it's an on or off, you can, hammer that thing as fast as you want almost, because it's always going to be unique. And you just get the transition states you have to clock. With parallel, you got to keep all 8 or 16 or 32, depending how wide your parallel is. They have to be kept in exact sync with each other. Otherwise, you start scrambling your data.
Exactly. And it also with serial, it makes it easier to do error correction too. Yeah, which is the key to making some of this stuff work. By the way, if you ever looked at a truly modern spinning hard drive, 20% of the data they're getting off the hard drive is actually an error. It's the error correction that makes it work.
ECC.
So yeah, because basically, they're writing the information so close to each other, they get failures all the time, and it can be up to 20%. Coming off the hard drive is a failure, but because of the error correction, it corrects it and gets it back working. In other words, if it wasn't for the fact that serial, the fact that you had error correction, which it just won't work. I know we've gotten off our subject here a little bit, but it's just shows how important serialized data is, and rotation of data and manipulation of it like that is a key component. Anyways, let's see, where are we at? Okay, so we've done the right. We've talked about that slide already, so let's move on to the next one, which is very simply, now that I got at least Steve up to a 4 on the DEF CON, I think we should stop here. And next lesson, we're going to go through and see how you can get your program to make decisions. And it's really going to be based on what we've covered so far between math and bitmulation. Those two things put together is how the computer will decide to do something. And yeah, believe it or not, those decisions allow us to make the games, or do the finances, or do all the fun stuff that you do on a computer. And if it wasn't for the fact that the computer did some sort of thing with making decisions, well, it'd just be a calculator.
All right, so I just want to make sure we are not talking about bit mutilization, right?
Right. Well, sometimes what I've seen people do is for what they call a game is it definitely falls in that category.
Okay. We want to manipulate our bits. We want to fiddle our bits. We can shift our bits. We can fiddle our bits, but we are not going to mutilate our bits. So,
Now, is there any questions from the people on the panel right now or in the chat that aren't assembly language programmers by trade type thing? That is
right. Well, what I would say we should do before we do that, let's take a quick break. And also, we have it looks like David Ladd and Grant Leedy are together in the same place. I've been noticing that their cameras are now in sync, and so I think Grant actually went to go visit David. So I think there's a little bromance going on here.
Really, Steve? Really?
Did Grant bring his buffing pad is my question.
Now we've got twice the David Ladd. Look at this. We got David in here twice.
Put on your stereoscopic goggles, people.
Yeah, we could never get him on video, and now we got double. I'm saying double vision.
Double the David Ladd. So
we shifted him left, and we left him in the carry, so now we've got both of them there.
Yeah, after the last 2 weeks I've had, I've been having a lot of double vision. So yeah.
Jeez.
All right, so good. So we're going to save the questions we're going to take a quick commercial break, and then we'll come back. But we have Grant and David are together, reunited, and it feels so good.
Oh, God.
Jesus.
Where's that mute button?
And then we will take questions and comments from the panel and from the people watching at home and stuff like that. Thank you, Steve. Actually, I followed almost everything. Fortunately, I do have a somewhat grasp on binary, so it's easy for me to see how these zeros and ones were kind of going round robin here. What do you keep holding up there, Mark Overholzer? Is that... Oh, okay. It's a tablet. Okay. For a minute, I thought it was like an 8-inch floppy or something you had there. So weird. All right. Cool. All right. So we're going to take a quick commercial break. Maybe not so quick. Who knows? But we'll take a brief break, and then we'll be back, and then we'll cover questions and comments on bit manipulation, and we'll see David Ladd in stereo. David and Grant. All right. So we'll be right back. Thank you, Steve Bjork. Thank you. You're too kind. All right. So we'll be back in just a minute.
I could make a comment.
Go ahead.
Please don't.
Go ahead, David. As David sips on his diet.
With half water and everything.
It's a David Ladd. Half diet Dr. Pepper, half water.
Yeah. It's like Arnold Palmer had a drink named after him. David Ladd's got one too.
It's like he ordered a Dr. Pepper, bit shifted it to the right, so it's half the size of.
Way to call it back.
All right, so getting back to Curtis's question right before the break, for those of you who are not fluent in binary, for those of you who do not often fiddle your bits and twiddle your other things, any questions, comments,
any clarifications needed?
Yeah.
Any DEFCON ones?
Anyone? No.
Manipulation is a transitive verb.
A transitive verb, meaning that it's in motion.
Mm-hmm.
Okay.
What are you, an English major? Or?
No, I have Merriam's dictionary up here.
Well, it's not a transient.
Look it up.
I learned never to cross the streams and never skip to the left.
That's right. So the arithmetic, the ASL doesn't work, right? The arithmetic, is that a word?
That sounds dirty.
That's like testes 1, 2, 3. Huh?
All right. At least I didn't get a Coco STD. So.
Hey, Rick, back in the early days when you're first learning about all the shifting around, did you run into what I talked about with the arithmetic shift to the left? How, hey, this doesn't work.
Refresh my memory. It was like shift to the left, and then like the bit would be lost.
Well, yeah, that's the thing is arithmetic is supposed to keep the sign bit signed, whatever it was. In other words, the seventh bit never shifted; it stayed the same. And,
right.
Yeah, and that's the thing is where the arithmetic shift to the right works, where the bit stays the same. But since they said, oh, well, we just won't put that command in. Not that many people use it. But because people like to expect to see it there, we'll call the logical shift to the left the same thing as arithmetic shift to the left.
Right.
Yeah.
I just read the directions and, I knew what it did. So.
Yeah, it's just.
That's a fake news instruction is what that is.
Yeah, I seem to remember also reading an article in some magazine that was talking about the 60-line instruction set, and the person was a little peeved at that too. It's like, it was definitely the engineers cutting corners.
Yep.
So
I love the bit about we only need a 64K address space because it doesn't make any sense to have a $20 processor controlling $10,000 worth of memory.
Yep. Well, even IBM had that mentality.
That was delightful.
When they developed the original PC, IBM PC, they designed it to access a maximum of 640K.
Yep.
Because they were shipping the machine with 64K. Well, we would never need more than 10 times the amount of memory that's on this computer. And sure enough, it didn't take long before people had to, and I know Stevie knew about this and dealt with it, going through and setting up iMemory so they could get their video games to operate.
Oh, yeah.
Because those stupid video game programmers used every bit that was on a normal computer, but if you added a particular I/O card to your computer and it needed a little memory for buffer, all of a sudden those video games didn't have enough memory.
Conventional RAM.
Yeah.
That was the key.
Memory has always been the pain in the side. I mean, every time I develop a game, I'm going, gee, I got to make it work in this. And, and when you start talking about things like the console stuff, every video game, 60th of a second, you could only transfer information of what is going to be updated that video game frame in the VBlank, and the VBlank would only let you do 550 to 6,000 bytes of data update per frame. I mean, that was the limit because you could not talk to video game memory during when the graphics processor was using it to display the graphic screen. So you could only use it during this VBlank period where it was turned off. And if you accessed it, you literally, the screen went blank. And, so it's everything was like limit of how much information you could update, how much information you had to update. It's limits. Nowadays, people just waste memory like crazy.
Oh, Richard had to go. Okay, I wasn't sure if Richard was going to be showing something off with his super high-powered magnifying lens, but Richard Lorbieski had to leave us. Goodbye, Richard. Eddie Serbinsky had to go in the live chat. So did Davey Mitchell. Yeah. No, it's pretty cool. It's good stuff.
Yeah.
You're when you're dealing with binary, because I've been teaching IP subnetting for so long, I kind of understand relative meaning of bits. So that's not a foreign concept to me.
Or the fact of data streaming.
Well, I didn't understand the science. I understand what data streaming is, but I didn't understand the science behind it. So
yeah.
Yeah, that's cool stuff.
Yeah.
What is we holding up here, Ron Delvo?
It's the 7th bit by Russell Brand.
Oh, okay. He's a funny guy. The 7th bit. Any other feedback or any other value-added comments on the whole assembly section there?
Did anybody else see anything else that we should talk about?
And
from the comments, because I wasn't monitoring those.
Oh man, there was so much going on. I'm going to back scroll here for just a minute.
I was just wondering, what we may have to do is next time I do a lesson, take one of you guys out there on the panel and have you monitor the comments.
Okay, so earlier when you were talking about the difference between bit shifting and bit rolling, Paul Fiscarelli says bit shifting can't hold a candle to bit rolling.
Well, it can hold a carry bit.
Right. And then Rob Inman was wanting to know, are we going to have a bit twiddling after dark tonight? So that's that's always a possibility. Earlier, Dave Phillipson, which Curtis had mentioned, was mentioning that you could use this bit shifting to reassemble bits that come in from the bitbanger port, which is basically a serial to parallel conversion, or vice versa, parallel to serial. Eddie Serbinsky said, thank you, Steve and Curtis. I'm assuming he means Steve Bjork and Curtis Boyle. David Mitchell said these lessons are very valuable. When we're talking about serial versus parallel, Paul Fiscarelli says it seems like serial can run at a faster frequency. Coco Man says you can shift your bits and fiddle your bits, but you can't fiddle your friend's bits. So
I would never want to do that.
Paul Fiscarelli says by comparison, serial is significantly higher and reliable at higher frequencies than parallel. Okay.
Yeah. One thing I wanted to say to it, look at what they did with USB. USB is universal serial bus, and it's in some information, and it keeps getting faster and faster. And I've got an old workhorse, let's see, HP laser printer 6P that I've had 20 more years, I don't know, and it's got the old-fashioned Centronics parallel port on there, and it takes forever to download a page from PDF into the thing. But my USB stuff, lightning fast, lightning quick. It just shows that going serial has its advantages.
Yes, it does. Yeah, it's just come full circle, because there was a time in the days of the old 8-bit PCs where for a while the parallel port seemed like a faster way to communicate than the serial port did when we were measuring things and,
yeah, because you could basically do the
kilobits per second.
One shot, but as the hardware got faster and faster, it became harder and harder to clock it and keep in sync. And then they discovered going back the old way, your speed limits were a lot higher.
Well, the other thing too is you had 8 wires traveling out with grounds on them like that. The propagation delays, capacitance, and other issues of all that cabling slowed down the data. And they found, gee, if you had a single wire, man, you could send that fast.
Yeah, and length of cable, that was a big one. Like in our old plant there, we had parallel printers, high speed 300, 600 line per minute ones. And we also had serial terminals running at 48 or 9600 baud throughout the plant. And parallel cables, you could only go so long before it did start losing sync and you get scrambled data. And the serial ones, we had like 200 feet long cables going out through the roof and up into the press area, and those terminals never had problems with that for the exact same reason.
Mm-hmm. So yeah, I mean, as an engineer in the old days, I thought parallel, bee's knees, greatest thing, faster data, stuff like that. But then when we really started clocking fast, I had to sit there and say, nope, we got to go serial. We can make this cable simpler, lighter, cheaper. It's kind of like the $6 Million Man, and
right,
make them stronger, faster.
The word for today is propagation.
Yeah,
propagation.
Yeah. Propagation delays. By the way, just to show you how important propagation delays are, the Cray computer, how it was so fast, it actually used propagation delays, how long it takes for electrons to flow from one point to another to do its high-speed mathematical calculations. They literally would put in wires a exact centimeter in size to do the calculation.
Wow.
So they're using the thing that was keeping us from going faster to make the computer faster.
Cool.
That's hard to get your head around.
DEFCON 3.
Yes.
By the way, if you've ever seen a picture of a Cray computer, it's built in a semicircle, and it actually looks like you've got things you can sit on that are in front of it. Those were the cooling units.
Kinda
But the
like
reason
this?
why they did it in a semicircle, it made the interconnection of the wires shorter.
Okay. Shorter bus, less. Yep. Very cool stuff. All right.
I got to play it with a Cray a few times. It was neat.
Did you? Do they make a lot of noise? There are a lot of fans.
Well, there's a lot of cooling going on. That's what's down below. Usually in most computer labs, the cooling's like maybe even in another room. And you've got the raised floor, not just to run the wires, but also to run all the cooling ducts.
Wow. Yeah.
I got to play with some interesting stuff at JPL.
Neat. To change subject here for just a minute, we have a couple of things coming on in the chat here. So number one, still on topic, Dave Phillipson was saying that if you look at HDMI, it's kind of a hybrid of serial and parallel. There's 3 or 4 serial channels in the data stream on HDMI. Now, Dr. X0079 is now asking us, has any of us heard of the Fujitsu FM77 because it has 2 6809 CPUs in it?
Yes, and it runs OS 9 beautifully.
It's like double David Ladd. We got double 6809. So you get some double floppies in there, and I think David would be a happy guy. Quad floppies.
Yeah. And Jim Brain is actually working on a multi 6809, 6309 board for the Coco 3 as well. So
what better than a brain to be working on it?
This concludes another episode of Coco Talk, the world's leading live talk show featuring the Tandy Color Computer. For all things Coco Talk, visit us on the web at cocotalk.live. We'd love to hear from you. Send feedback, suggestions, even segments via email to cocotalk@cocotalk.live.
Coco Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Coco Talk is rocking the 8-bit world.
Consider supporting the show with a purchase of merchandise from our retro swag shop at 8bit256.com. If you'd like to become a patron of the show, click the Patreon link at our website at cocotalk.live.
Coco Talk is rocking the 8-bit world, keeping the Tandy flame alive. We may be mocked, but we'll never stop, 'cause Coco Talk is rocking the 8-bit world.
Coco Talk would not exist without the community, its cast, crew, and contributors. Thanks go to Curtis Boyle, David Ladd, Mark Overholzer, Grant Leedy, Bruce Moore, Nick Marentes, Ron Delvaux, Rick Adams, Jason Reichert, Richard Lorbieski, Jim Brain, Tom C., Rob Inman, Mark Bosley, Brian Joyce, Ken Reichert, David O'Connor, Brian Weasler, Terry Steggy, Nick Marotta, John Strong, and many more, especially to Steve Bjork for production suggestions and James Different-Daffer for making my head explode.
Please help support the cocoa community by visiting some of its various contributors. A list of resources is available at imacoconut.com. That's imacoconut.com. The Cocoa Talk theme song is copyright 2008 by D. Bruce Moore and Greg Sheeler. Mixed, mastered, and produced by D. Bruce Moore.